My name is Xiaotian Liu, and this is my final project presentation about a paper, Intelligent Low-Frequency Control for Improving Wind Power Penetration in Power Systems. For the course, Smart Grid, I did not grant Professor May permission to make this video publicly, but agreed to allow access to fellow students in this course. The presentation includes five parts. The first is introduction. The second is relation to the course material. Third one is simulation and performance evaluation of this paper. The fourth one is comparison with the prior research of this field. And the last one was the extension was about this course and these techniques introduced in the paper. Begin with the introduction part. Nowadays, we face the challenge of wind power variability. Wind power fluctuations. Wind power is a clean and renewable energy source. It is inherently variable due to the unpredictable nature of wind. This variability poses significant challenges for power grid stability, as it can lead to frequency fluctuations that necessitated robust low frequency control, which is LFC mechanisms. So what is low frequency control? It's a critical process used to maintain the stability of the electrical grid by regulating the system frequency and power balance, ensures the proper functioning of the power grid despite changes in load demand or generation, like the wind power, especially the integration of large-scale wind power into the grid introduces significant variability, which can result in great frequency deviations. These deviations can compromise the reliability and stability of the power system, making it crucial to develop enhancing LFC strategies. As for the problem stated, the objectives of this paper is to enhancing LFC for renewable energy. This study explores and proposes an intelligent LFC mechanisms that can effectively handle the challenges posed by the integration of large-scale wind power into the grid. And also, this paper introduces cloud-based PI controllers. It introduces an enhanced cloud-based PI controllers that utilize adaptive parameter tuning to accommodate the randomness and unpredictability of wind power, aiming to improve grid stability and frequency control. For the next part, let's explain how this paper related to the course material. Firstly, relate to the frequency control mechanisms. The course emphasizes the role of primary, secondary, and tertiary controls in maintaining grid stability and operational efficiency. The paper builds upon these concepts by addressing the integration of wind power into the LFC framework, particularly focusing on the cloud-based PI controller. Let's review the three kinds of controls. The primary controls is the fast response, typically within a few seconds to tens of seconds. It's about automatic response of turbine governors in power plant to frequency deviations. When frequency decrease, the governor opens the valve to increase power output. When frequency increase instead, the governor reduce power output. And for the secondary control part, is about restoring the system frequency to its normal value. A centralized control system monitors the grid and sends adjustment commands to specific generators. It relies on PI controllers or modern algorithms to eliminate steady-state errors. When we talk about secondary control, it includes the AGC, which is automatic generator control. AGC is a key mechanism for balancing power and frequency. It's used in the secondary control in power system, centralized system designed to automatically adjust the output of select generate units to maintain the system frequency at its normal value and control the power exchange between interconnected areas, measures the differences between the actual frequency and nominal frequency. The difference between actual and scheduled tie-line power flows in multi-area systems is also AGC's work. Adjust the power output of selected units. The AGC can eliminate frequency deviations and tie-line power errors. The third one is about grid stability with renewables. The course deals with challenges of renewable energy integration, such as intermittent power output and their effect on grid frequency. The paper emphasizes on cloud model-based adaptive control, which directly tackle these challenges by enhancing the robustness and flexibility of LFC systems. Another relation to the course is about real-world relevance. The application of cloud-based PI controllers extend the course's exploration of techniques such as AI and advanced algorithm for improving the grid operations. It's about predict the price, the frequency, and all the parameters of the grid. The paper highlights the practical significance of these innovations in the increasing wind power penetration while ensuring the grid reliability. The third part of this presentation is about the simulation of the paper. In the simulation, the paper modeling the power system into two area interconnected power systems, which models a two-area interconnected power system with wind power using the MATLAB Simulink. This model allows for the simulation of various scenarios to evaluate the performance of proposed cloud PI controller. And it incorporating wind power generation, like the figure 1 shows. The wind power generation is incorporate into the model, simulating the variability and unpredictability of the wind power. This setup enables the evaluation of the controller's performance in managing frequency deviations under changing wind power outputs. As you can see here, the actual wind speed is measured wind speed at the location of the wind turbines. And the predict wind speeds is the wind speed forecast or estimate based on the weather models. And each wind turbine or group of turbines is modeled with the transfer function like this. where the K subs WTGI is the gain factor of the ith wind turbine or turbine group. The T subs WTGI is the time constant representing the response time of the turbine systems. And the S is the Laplace variable representing frequency in the Laplace domain. The output here of dynamic models are summed to calculate the total wind power deviations. And here's the simulation result. As you can see here, the result indicates that the cloud PI controller outperforms both conventional and fuzzy PI controllers in terms of reducing frequency deviations and stabilizing timeline power flows. As you can see, the blue line is less fluctuated than the red line and black line. Here's the thing. It indicates that the cloud PI is the most stable. Actually, the performance of cloud PI controller is evaluated based on key indicators such as frequency deviations, timeline power flows, and so on. As you can see, the power deviation in timeline, the cloud PI controller is the most stable ones. It fluctuates the less. And the fourth part is comparison with prior research. First is the limitation of fixed parameter design in the traditional PI controller. The traditional PI controller with their fixed parameter design struggle to adapt to the variability of high-scale wind power. This limitation has led to the exploration of more adaptive and dynamic control mechanisms. It's kind of stable parameter, so it's not that flexible for some changing environment. Also, the performance under variable local conditions is limited. Under variable local conditions, traditional PI controllers may fail to maintain great stability, highlighting the need of enhancing LFC strategies that can handle the dynamic nature of wind power generation. All these two drawbacks are caused by the unstability, the unpredictability of the wind power. The traditional fuzzy PI controllers has the limitations. It provides some level of adapt it provides some level of adaptabilities. Their performance is still limited by the inherent randomness of wind power. But it also improved adaptabilities by offering improved compared to the traditional PI controllers. However, they still fail to full account for the random nature of wind power because the wind power is unpredictable, so the generation is also unpredictable. So it's necessary for further advancements in LFC technology. By introducing the cloud PI controller as a novel approach, it incorporating real-time adaptability. The cloud PI controller represents a novel approach by incorporating real-time adaptability and uncertainty modeling. This allows a better handling extreme wind fluctuations. Also, enhancing grid stability with cloud-based control. The integration of cloud-based algorithms and adaptive parameter tuning in the cloud PI controller enhances grid stability. and frequency control, making it a promising solution for future power systems. As you can see in the figure here, the two set of inputs are error-related variables for components of the systems, and the cloud generator CGE here combines the inputs to generate output for the subsequent controllers CGP and CGI. To use the group functions, it generates proportional control signals based on P and the parameter mu. To summation, the output delta P and delta I are summed to form a composite control signal here. And for the governor part, it uses the composite signal to regulate the system, ensuring appropriate frequency control. This model likely uh, it implements a fuzzy or soft computing approach within the cloud architecture to approach proportional integral control. The merits of the Cloud PI controller is about adapt is about dynamic adaptability. The dynamic adaptability of the Cloud PI controller is a significant advantage over traditional and fuzzy PI controllers. As seen in the simulation part, its ability is to adjust parameters in real time, allows for effective management of wind power variability. Another result you can see from the simulation part is that its superior performance in simulations. The performance of the Cloud PI controller in simulations, particularly in reducing frequency deviations and stabilizing timeline power flows, underscores its potential for handling high level of wind power integration. Also, the new designed LFC system and Cloud PI controller study has shortcomings. One shortcoming is that its over-reliance on simulations. The findings of the study and the paper are based entirely on the simulations, which can be useful but do not fully capture the complexities of real-world grid operations. This limitation raises questions about the controller's performance in practice. Another shortcoming is that its lack of real-world testing. The lack of testing in the physical setups or hardware in the loop environments means that the controller's effectiveness in real-world scenarios remains unproven. Further research and practical testing are necessary to validate the controller's performance, except for the simulation. The last part is about the extension of this study. The first one is validation with physical systems as discussed below. It can be one of the directions for further work. Another direction for the further work is expanding multi-source integrations. Besides the wind power generation, it can also explore the controller's performance in grid with a mix of renewable sources such as solar or hydro would enhance the generalizability of the system it designed in the paper. The third one is incorporating with machine learning. Integrating machine learning algorithm to refine the cloud model rules dynamically could address operators' bias and improve adaptability to unforeseen conditions. And thank you. That's all I'm presentation.